Thanks for joining us for the first video for Chapter 5, which is about getting introduced to stereochemistry. And this is really the last chapter where we're kind of just learning about the sort of new language we use to describe organic molecules before we get into talking about organic reactions. Because biology happens because biochemical reactions happen, and all of those are organic reactions. And similarly, how do we make drug molecules? It's all by organic synthesis, organic reactions. So, and a lot of those molecules are chiral, and that's this word that actually means handedness. The word chiral comes from the word hand, I believe, in Greek. And the idea is like your right hand and left hand, they're mirror images of each other. They're basically the same, but they're different, right? They're not superimposable. They're not identical because your hand is a chiral object. And chiral things can bend light, so that's a good way to measure how much chiral material you have. And chiral things, right-handed and left-handed, we need to have a nomenclature to sort of name them when they're chiral. And then what happens when there's a bunch of different sources of chirality in a molecule. And then finally we'll talk about properties of chiral type of molecules in the end. But before we start talking about any of that, we need to be able to sort of categorize all those chiral molecules. So let's talk about isomerism in a little more comprehensive way than we have in the past. So isomers, remember, just means they're two isomers have the same formula, but they're somehow different. Now, the way that is different, they're different, has to do with connectivity. Then, if the connectivity are different of the two molecules, then they're constitutional isomers. Or sometimes they're also called structural isomers. Right. For example, these two molecules, if you count the number of atoms, you'll notice that they both have the exact same molecular formula, but their structures are different, as in the way the atoms are connected. Like this sp2 carbon is connected to two methyl groups, but this sp2 carbon is connected to an ethyl group, so that's different connectivity. If they have the same connectivity but they're different, then they're some sort of stereoisomers. Okay. And the reason why we're going to go through this sort of diagram is because there's many different types of stereoisomers. Some of those we've encountered before already, like if the two molecules are different only by rotation of a single bond, then there was a word for that, right? That hopefully you still remember, and that of course would be conformers or conformations, or conformational isomers, you could say, but conformers for short. Maybe that's kind of squished. Okay. Now, if the difference is not just because arising from the rotation around a single bond, then there's some sort of configurational isomers. Now, this particular word is not very well used, so configurational isomers, I'm not as keen on you knowing about that, but if the two molecules are different because they're mirror images of each other, but they're different, then those are called enantiomers. Okay. And if the two different configurational isomers or stereoisomers are different, but they're not mirror images of each other, then they're called diasteromers. Okay. Some examples, enantiomer examples. If you looked at that molecule in the mirror, you would see this, and that would be an example of enantiomers of each other. We didn't talk about the conformer example. These two would be related as conformers. Now, diasteromers, what would they look like? If you had something like this, these two have the same connectivity as in these two carbons are connected to bromines, these two are connected to bromines, but they're different and they're not mirror images of each other, so they would be diasteromers. And this categorization really becomes important for you to be able to classify them, because the molecules that are related as enantiomers would exhibit different types of property relationship than diasteromers and so forth. And so this is really important to understand chemical for chemistry. Not to mention, if you're in biomedicine, right, like, or a pharmaceutical area, different enantiomers, even though they're just mirror images of each other, can confer totally different bioactivities on people, and we'll talk more about that. So okay, I need you to be able to categorize the relationship between two molecules. So that diagram is really, really important. Now, I just want you to know from that diagram, first of all, that enantiomers, these things, are chiral. Okay. And what does that mean? This means having a mirror image that is not superimposable. For example, like something like a spoon would not be chiral usually, unless there's some chiral markings on there. But something like your glove would be chiral, right? Like it's got a mirror image that's not superimposable. So here's an example of an achiral or not chiral molecule. And the reason why we could say that is, like, if you think about this molecule, I'm just gonna kind of draw it in a like a 3D suggestive manner, but I want you to see that these are the same molecules, right? If there's a mirror in the middle, if if you can imagine that, the mirror image would look like this. But the thing is that these two are actually identical. They're superimposable, right? That word just means you can put them on top of each other and they're identical. Now, what about a molecule like this? So let's do a similar drawing. Notice the only difference is hydrogen is replaced by a fluorine. Okay, so hopefully you would agree that these two are the same drawing. So now let's think about drawing the mirror image. And at first glance, maybe they look similar, they look the same, but I want you to either do this in your mind, see if you can move this around to superimpose it on this, or better yet, I know you might be sick of hearing me say this, but if you make both of these with molecule model kit, which this would be a really, really important exercise, please do so. You'll notice that the two are not identical. They cannot be superimposed. So these two are non-superimposable mirror images. So that means these two are enantiomers of each other. That's their relationship. Okay. So that's an example of a chiral molecule, and I want you to notice how this chiral center is this carbon. And it's got 4 different groups attached to it. And that's one of the things that will make something a chiral molecule, chiral object. When it comes to a molecule, if carbon has 4 different things attached to it, that makes it a chiral center, and the whole molecule is now chiral. A little bit more generic term is stereocenter, which includes chiral centers like the one we just talked about. But stereocenter, sometimes people call this stereogenic center, because if you have a stereocenter, you're going to have a stereoisomer, excluding conformers. I should say you're going to have some sort of configurational isomers, whether enantiomers or diasteromers. Okay. And what is a stereocenter? When you have, if you interchange 2 of the attached groups on that carbon, that leads to a different stereoisomer. Okay. That's what makes it a stereogenic or stereocenter. So for example, here's a molecule with an olefin or alkene in it, and this is actually not chiral, the olefinic carbon. By the way, alkene carbons, we would call them olefinic carbons. Alkene, olefin are kind of synonymous. Okay, I want you to pay special attention to these 2 carbons. Okay, they're stereocenters. Okay, maybe I'll say. How do I know that? Because if you interchange these 2 of these attached groups, right? interchange those two just on one side. You will get this molecule, and these two are not identical. Therefore, they're related as stereoisomers, right? Specifically, these two actually are diasteromers. Because they're stereoisomers, configurational isomers, but they're not mirror images of each other. And when it comes to the double bond being trans, meaning two groups are opposite of each other or cis on the same side, that is often called geometric isomers as well. When it comes to these olefin or sp2 carbon stereoisomers. Now, that's one type of stereogenic center, is when you have an olefinic carbon. Another is when you have a chiral center, like we talked about a second ago, which is a really important concept. And sometimes we call these asymmetric carbon, but here are some examples of those. Here's a chiral center, here's a chiral center. Why is that? Because this carbon has a methyl group, ethyl group, and 1, 2, 3, 4 butyl group, and not to forget that there's a hydrogen. So there's 4 different things attached to it. By 4 different things, that we don't mean like 4 different elements. These are all carbon elements, but different groups, right? So similarly, this carbon here is a chiral center because it's got a methyl group, and then olefinic carbon, and a methylene CH2 alkane carbon, and of course a hydrogen. So that's got 4 different things attached to it, which makes it a chiral center. So that means both of these molecules are chiral. In fact, if you want to verify that, you draw the mirror image of it, and it would not be superimposable. Now, I'll draw another example. Sometimes at the beginning, some students might get tripped up by this, but this molecule I just drew is not chiral, and this is not a chiral center, because it's got methyl hydrogen, so those are 2 different things, but these 2 methylene or CH2 groups are identical, and so it doesn't have 4 completely different groups attached to it. So this is not chiral. So this would be achiral. These 2 would be chiral. Okay. Just so you could get some practice of this, see if you can spot how many chiral centers in this steroidal molecule. That's a nice review of the concept we learned in the last chapter. Actually, I need to move this down a bit. So it's a little short for space here. Okay, so maybe pause the video and see if you can count how many chiral centers you see in this molecule. This is cholesterol. Okay. Now, if you unpause the video, I'll circle the chiral centers. Okay, and that's it. No other carbons are chiral centers. So this has 8 chiral centers. Okay, maybe I'll go over some of them. Like, for instance, this this carbon is a chiral center because it's got an OH and a hydrogen, And then you might say, well, it's got two methylene CH2 groups here, so aren't those the same? But this CH2 is attached to an olefin, whereas this CH2 is attached to another CH2. In other words, these two groups are not completely identical, and so therefore this is a chiral center. Okay, and you can kind of go through each of these carbons I marked, and you'll see that they have four different things. But like, for instance, this carbon is not a chiral center because it's got two methyl groups which are identical, right? So if there's two identical groups attached to a carbon, that's not a chiral center, which, by the way, I hope this makes sense to you, but because this has at least one chiral center, in fact 8, but if you have one chiral center, this molecule is said to be chiral. This is a chiral molecule. And that stereochemistry plays a big role in its biology. Anyway, we'll pick it up from the next section next time.